Hello everyone, thanks for the intro. So I'll present our work on influencing factors on touch biometrics, so on the idea of recognizing people based on how they touch. And I would like to start with a basic motivation. So let's say this is your phone, and it's lying on the floor because you lost it, unfortunately. And maybe it's even worse, and you lost it in an unlocked state. And now anyone could pick it up and read your emails, view your pictures, and so on. And of course, we want to prevent this. And one idea of doing this is to use what's called implicit continuous authentication. So the phone observes how you interact with it, and if this deviates from your usual behavior, it may raise alarm or lock itself. And in this work, we in particular observe touch behavior. And so to summarize, the idea is that the phone kind of asks itself consistently, is it still you who's touching? Now, taking a step back, if we want to do this, of course, we need to observe touch behavior to recognize if it's you or someone else. Looking at related work, there are a bunch of interactions that we could observe. So, for example, there's work on keyboards, so observing touches that occur while typing. Or you could combine this with a primary authentication method, for example, with the Android pattern unlock. So in this case, you don't just observe if the correct pattern was entered, but also the way it was entered. There's also work on using multi-touch gestures to identify users based on touch interactions. And then there's this work from Su et al. Presented at SOUPS 2 years ago, who compared a bunch of different touch interactions with respect to how well they could recognize users based on these interactions. And they compared things like zooming and sliding and handwriting and pin entry, and you can see their study interfaces on the slide. Now, if we look across these related projects, we see that we can come up with a comparison of interactions, and that's also the essence of Su et al.'s work. So we could arrive at conclusions like we can better recognize users based on touches that occur while writing on the screen with the finger than while pinching or zooming. So we can compare between these things. However, there is no comparison yet between the different UI properties for one interaction. So we might think that maybe the way the interface looks like, maybe the size of the buttons and so on, might influence if users behave more consistently or more characteristically. And so this is what we're going to study in this work, namely the influence of elementary UI properties in combination with two-hand postures on touch biometrics. And in particular, we look at different target locations and shapes and sizes. And I will explain this in more detail in a minute. And to keep things in a manageable number of variables, we limit this study to the most fundamental touch interaction, namely a simple tap, so no sliding or writing or stuff like that. Okay, so this slide is an overview over our approach to measuring touch individuality, and it also serves as the structure for the rest of the talk. So we have 4 steps. In the first step, we observe user behavior, of course, and we conducted a user study that has 2 sessions, and there was a gap of a week between the sessions. And in each session, we present users with these targets, and we ask them to hit these targets. In the second step, we model user behavior. So we represent users with a model, and I will explain the model in more detail later. And so basically, this model captures the targeting behavior of the users. And we train these models on the data from the first session. Then in the third step, we want to recognize users. And there we feed the data from the second session to the models trained on the data from the first session and try to see if we can predict the correct user or not. And this captures an aspect of consistency because we train and test across weeks. And then in the fourth step, we can measure individuality with any metric that we can relate to the output of the recognizer. So, for example, just identification accuracy. So the ratio of cases in which we would predict the correct user. And then we get a number on how individual users are, or we can interpret it as such. So in the first step, we start with a study condition like aiming at small targets in the top left corner. And then in the fourth step, we get like maybe 90% accuracy, and we can compare that for different conditions. Okay, so let's go through these 4 steps in more detail. The first one was observations. So this is the data set we use. It contains 4 target types, which you can see on the slide. A crosshair target. In practice, this could be something like pointing on a map. A key size target, which is, well, like a key on a typical smartphone keyboard. An app icon size target, and a full width target, which is basically 1D because only the vertical dimension matters to determine whether you hit the target or not. These targets were presented in 400 locations, placed in equally spaced grid across the screen, and they were presented to participants in a random order. We observed 2 hand postures, thumb input, which was holding the phone in the right hand and touching with the right thumb, or index finger input, which was holding the phone in the left hand and touching with the right index finger. And the phone was always held in portrait orientation. We had 24 participants, and they completed 2 sessions, which amounts to about 150,000 touches. So the second step was modeling. So starting with a single observation here, so this could be a task and study. So we display this crosshair target, and we ask users to touch on it. And of course, we're not 100% accurate, and so there's a difference between the touch location and the target location, and we call this error and touch offset. And we might represent it with a vector like this. Now, if we repeat this for the 400 target locations, we get a data set like this, and then we can apply a regression surface, basically, which yields a model that could be visualized like this. And so this model, if you give it a touch location, it predicts where a user would want it to touch, based on the past behavior. Now, in related work, this is used to improve touch accuracy, and we want to use it to recognize users. So this is how this works. So in the first step, we recognize users. So again, we have a targeting situation like this. We have a target location and a touch location. Now we want to find out who is responsible for this touch. And in the simple example, let's say we have a user A, and we have a model for user A trained on user A's previous touches, and feeding the touch location to the model might predict that the user wanted to touch here. And for user B, we get a prediction like this. And then we can work out who's more likely to be responsible for the touch. In this scenario, it's user B, because the target is more likely given the predictive distribution of model B. Or in other words, user B's past behavior better explains the current behavior than the behavior of model A. Okay, and the fourth step was measuring, and that leads us to the results. So let's see what have we measured indeed. Here's a basic comparison of the study tasks. So let me walk you through the plot. So the vertical axis gives you the identification accuracy, so the number of correct predictions. And the horizontal axis is the size of the group. So on the very left-hand side, we have pairs of users, 2 users. Like in the example I've just shown on previous slide, this is basically saying, is it user A or user B? And then to the right, we have 20 users, and this is averaged over many random draws of groups of that size. And this is interesting because, of course, it's much easier to find something that's characteristic for a specific user if you just have 2 users compared to a larger group of users. And then I annotated the different study conditions on the slide. And so to summarize this here, we find that smaller targets lead to more individual targeting behavior compared to larger targets, and thumb input leads to more individual targeting behavior compared to index finger input. Another observation is that we can't really recognize users based on touches at these full width targets. Looking into the data in more detail, we found that because these targets are so large, users have such a large area to choose from, and thus they are very inconsistent, and then you can't really find something that's individual to a particular user if they are very inconsistent. A second analysis we conducted with respect to relevant screen locations, and with relevant I mean which areas of the screen are most relevant to describe users' individual targeting behavior. And so to explain this, we have to look back to our model. So if you remember, we had this data set, and we trained a model on these touches. Now we use a slightly different algorithm, which does not use all of the training touches to represent the user's pattern. It throws out most of the touches and just keeps some that it finds relevant. So it's an optimization routine. So for example, it might decide that given all these 400 touch locations, it just needs these 3 to represent the same model as before. And now we can look at the distribution of these relevant touches across the models of all users for one study condition to find out where most relevant touches are. And so, for example, for thumb inputs aiming at crosshair targets, we get a histogram like this. So the higher the peak the more touches are relevant in this area. And so we can do this, of course, for all our conditions, as indicated in the back of the slide. And to summarize, we found that the edges and the corners of the screen are more relevant than the center. And this matches results from related work for some of the conditions that were examined in related work as well. Okay, so to summarize here, we've seen that behavior is less consistent for larger targets. Thumb input is less accurate but more individual than index finger input. And touches near the borders of the screen are more descriptive of users' individual targeting patterns than touches in the center. There are some other results in the paper as well. Now the question, of course, is what can we do with this information? And I want to spend the rest of the time to talk a little bit about that. So one idea we propose in the paper is to analyze UIs with respect to touch biometrics. And in particular, we could try to estimate how useful a given UI is if we want to recognize users with touches that occur in this UI. And so given a UI, and by given I mean you would give me a description in terms of bounding boxes and a little bit of additional information, we could train a model based on our data and study models where users would touch in this UI. Here's an example for a home screen. And this model is probabilistic, so it's basically a density of touches, so we can sample from this model. In other words, we can simulate touch behavior for this UI with strong limitations, of course. And then we can feed these simulated touches into our 4 steps to then again see how well we could measure, could identify users based on these interactions. Of course, we should be careful with interpreting this because simulated behavior is not as complex as real behavior. But we can compare these results between different interfaces. Here's an example for exactly that. So here's a list view from Android, here's a home screen, and here's a keyboard. And output might look like this. So again, we get a plot that predicts how well we can recognize users after a certain number of touches. And in this example, the prediction matches our expectations based on our own manual analysis and the results of related work. So you can fairly well recognize users based on typing behavior, which we know from related work as well. And you can't really recognize them based on touches at the list, which only uses these large targets, as we saw in the previous analysis. And the home screen is somewhere in the middle. Okay, so to conclude, I want to show 2 sets of implications as our takeaways. So the first is with respect to UIs. So if we want to improve touch biometrics, we should use compact UI elements. We should place them near the edges of the screen. And we should use thumb-friendly layouts because the thumb was more individual than the index finger. Now, I want to emphasize very strongly here that I'm not saying that as an interface designer, you should optimize your interface for touch biometrics. Obviously, you want to optimize for usability or user experience. But if you know that you also want to use touch biometrics on that system, you might keep these in mind. So, for example, what you can do is if you take an interface like this is the Google Calendar app, you have several targets that you could observe. And according to these guidelines, you might focus on touches occurring at these targets and not at the actual calendar entries, for example, because they are so large and in the center. So instead of changing the UI, you could use these guidelines to optimize what you're looking for when observing touches. Okay, another set of implications is with respect to actually building such touch biometric systems. What have we learned in this regard? So first thing, obviously, is that we need to consider context and our context conditions with the hand posture and the UI elements. So those should be included in touch biometric systems. And this implies that we need to get this information, which means that we might want to look out for combinations with other systems running on the device. So for example, there are several related projects that show methods of recognizing hand postures based on touch behavior, and these would go well together with touch biometric systems to give you the actual posture. And the OS could provide information about the currently rendered UI. So for example, in Android, there is this accessibility service which can give you some information about the current interface elements. And the third implication is to use multi-model methods. And this takes inspiration from work by Yin et al. Presented at CHI 3 years ago. They used a hierarchy of models to adapt keyboards to the individual typist to improve your typing. And we think that this could also be useful for identifying users based on touch behavior. And the idea is that you start with a general user model, basically the model that we've seen throughout this presentation. And as you observe data from specific postures, so for example, thumb touches, you can train a thumb-specific model for this user. As you observe data from target-specific touches, you can train a target-specific model, and you could even combine the two. And with that, I thank you for your attention, and I welcome your questions.
Hi, Cameron Fanning from the University of Edinburgh. This is very interesting work. I'm curious how what the user was doing prior to attempting to touch this particular point impacts the results. So we know from things like GOMS modeling that if I'm trying to move between 2 points quickly, for example, my behavior will be different than if I'm trying to move between a large point, a small point, or any of these sorts of activity. Did you take that into account at all?
Yeah, very interesting question. So we didn't analyze that in the paper. On the same data set, I played around with it a little bit, like in terms of using the last 2 touches to predict where the user is touching, so not recognizing the user, but trying to see if I could improve the prediction. There wasn't much of a difference in this regard, but certainly an interesting direction. It would need, I mean, in the study we counterbalanced the orders, but for one target type we had the 400 locations in a row. So to get that, we might want to have the transitions between different target types as well, which would be interesting. Yeah. Thank you.
Hi. Lori Craner from Carnegie Mellon and the Federal Trade Commission. I was wondering, in thinking like an attacker, if you were to implement some of your suggestions and to focus onto the smaller targets and things like that, would an attacker be able to just avoid touching those types of targets and only use the larger targets to get whatever they want to get off your phone?
Thank you. Yeah, that's a very interesting question. So if the attacker knows about the system running, then I guess you can do that. I mean, you could argue that if this is not overt, then you don't really can avoid that. But yeah, there might be navigation paths that you might abuse to get to your goal. I would say that the number of touches that you need to observe is, at least in this, just using this single touch feature, we just use the touch locations, fairly high anyway. So like 100 to 300 touches, which like 1 to 2 tweets before you could recognize someone else with that feature alone. So in practice, you probably want to combine this with other touch features, which has been done for typing, for example, and then especially for typing, which might be one of the main attack cases, like sending compromising messages from your account and stuff like that. I would be optimistic that with other touch features, you could bring it down to a small number of touches that's suitable, and that would also avoid that, because if you limit it to a keyboard, for example, then you can't really avoid the targets. Yeah.
Hi, Ross Wong, Google. I was wondering if you observed any improvement or sorry. I was wondering how the hand sizes of the participants may have affected the similarity.
So we measured the hand size by putting it on a scanner and then copying it, and the measure on the paper. We didn't find differences with respect to identifying them, but with respect to the targeting accuracy. So basically, if you have larger hands, you can more easily reach targets in the top left corner, which is not that surprising. So there were some differences between different hand sizes, but not with respect to recognizing people. But of course, it might be useful as an additional feature if you can infer that.